The theory of the multiverse suggests that our universe is not the only one that exists, and our universe is only one of the infinite universes that could exist. But what does science say about this? Could other universes exist? If you want to know the answer, watch this video until the end. In theoretical science and modern cosmology, an intriguing concept emerges that challenges our traditional perception of reality: multiverses. This theory raises the possibility that multiple universes exist beyond our observable cosmos. Over the years, various conjectures have emerged, each with its own premises and mathematical underpinnings, seeking to answer deep questions about the nature of the universe and our place in it. Where does this theory come from? In 1957, American physicist Hugh Everett proposed one of the first theories related to multiverses. Known as the many-world interpretation or the parallel universes theory, this idea is based on quantum mechanics. According to Everett, every time a quantum event occurs, the universe splits into multiple branches, thus creating a multitude of realities in which each possible outcome manifests. This theory suggests infinite parallel universes, each with its own version of reality. In this theory, every decision a person makes creates a new universe, one where the decision was made and another where it never happened. Thus, if you decide to wear your favorite shoes today in the morning, there is a universe where you choose a different pair of shoes. Another prominent theory is the one proposed by the British theoretical physicist David Deutsch in the 1990s, known as the multiple universes interpretation. This theory is based on the idea that the universe follows the laws of quantum computing and can therefore be seen as a vast quantum computer. Deutsch suggests that by performing calculations on this cosmic computer, we could access different universes within a multiverse. It's like going to YouTube to watch your favorite videos. Still, instead of finding the video from your favorite channel, you find an infinite amount of videos from different versions of your favorite channel. Crazy, right? One of the most recent and controversial theories is the cosmological landscape, or eternal inflation, proposed by the American physicist Andre Linde in the 1980s. This theory postulates that the universe undergoes a process of infinite inflation, generating an infinite number of bubbles or bags of space-time in constant expansion. These bubbles could house a different universe with its own physical laws. According to this theory, our observable universe would be only a tiny part of a vast and ever-growing multiverse. While multiverse theories have captured the imagination of many, it is essential to note that they lack direct empirical evidence. Since observation and experimental verification are fundamental pillars of science, some scientists are skeptical of multiverses. However, despite the lack of concrete evidence, these theories are based on strong mathematical foundations and derive from well-established concepts in theoretical physics. Is there evidence that other universes exist besides ours? Current science addresses the question of multiverses from different angles. On the one hand, research is carried out in observational cosmology to search for indications of the existence of other universes. Traces left by previous cosmic events such as microwave background radiation or galaxies' distribution are studied to find anomalies, including parallel universes' influence. On the other hand, theoretical physics delves into the realm of mathematical equations and theories to explore the possibilities of multiverses. Complex mathematical models are developed that allow the implications of these theories to be explored, and computational simulations are run to better understand how multiverses might work. Scientists who have made significant contributions to this field have included such prominent names as Brian Greene, Max Tegmark, Alan Guth, and Leonard Susskind. These researchers have approached the issue from various perspectives, such as string theory, quantum gravity, and inflationary cosmology, seeking to unify the theoretical foundations of multiverses. However, despite the enthusiasm and theoretical advances, the lack of concrete evidence has led to an ongoing debate in the scientific community. Some argue that the multiverses are metaphysical concepts rather than verifiable scientific theories and could be considered speculation without an empirical basis. Others argue that, although we do not have direct evidence, Multiverses are valid scientific hypotheses that must be rigorously explored and examined. Before moving on, don't forget to subscribe to my channel if you haven't already. Make sure to hit the notification bell so you don't miss out on our daily videos. If there is no evidence, why is this possibility being studied? It is important to note that science is constantly evolving, and what may seem improbable or speculative today may be supported by new observations or theories tomorrow. A prominent example is the theory of black holes in the universe. In the 1780s, the British astronomer and clergyman John Michell and the French mathematician Pierre-Simon Laplace raised the theoretical possibility of the existence of celestial objects so massive and compact that their gravitational pull would be so strong that not even light could escape their force. However, the technology and observations necessary to confirm this hypothesis were unavailable at that time. For much of the 20th century, black holes were considered speculative, and some scientists doubted their existence. It is not until the 1960s that advances in general relativity and astrophysics provided a greater theoretical understanding of these objects. Finally, in 1971, the first black hole candidate, Cygnus X1, a binary system that emits X-rays irregularly, was detected. This observation provided indirect solid evidence for the existence of a black hole, and finally in April 2019, with the help of the Event Horizon Telescope, the first image of a supermassive black hole was captured in the center of the galaxy M87, located about 55 million light-years away from Earth. Since then, numerous black holes have been found in our galaxy and other galaxies, and they are now considered a fundamental part of cosmology and astrophysics. Another prominent example is the theory of the existence of neutrinos. In the 1930s, theoretical physicist Wolfgang Pauli proposed the existence of a very low-mass, neutral subatomic particle that barely interacted with ordinary matter. Pauli postulated the existence of neutrinos as a solution to the problem of energy conservation in specific nuclear decay processes. Initially, this idea was received with skepticism, since there was no direct evidence of the existence of neutrinos, and they were not detectable with the technologies available at the time. However, in 1956, physicists Frederick Rains and Clyde Cowan experimented with the Savannah River nuclear reactor in South Carolina, United States, where they detected neutrinos for the first time. Cowan's experiment detected neutrinos from the disintegration of neutrinos generated by the nuclear reactor. Using sensitive detectors, they could capture the interactions of neutrinos with water and observe the characteristic signals of these interactions. This experiment marked a milestone in particle physics. It confirmed the existence of neutrinos, which had significant implications for our understanding of the standard model of particle physics and the nature of the universe. These examples illustrate how a scientific theory can initially emerge as speculation based on solid theoretical foundations, but without direct empirical evidence at the time. However, with the advancements of technology and observations, evidence can be obtained to support the theory and confirm its validity. It is important to emphasize that science constantly evolves and that theories can be modified or refined as new evidence and knowledge are obtained. Ultimately, the study of the multiverse invites us to question our assumptions about the nature of reality and deepen our understanding of the universe we inhabit. Multiverse theories posit the existence of multiple universes beyond our own, each with its own physical laws and realities. Although these theories lack direct empirical evidence, they are based on sound mathematical principles and are explored by prominent scientists in various fields. In our search to understand the vast cosmos surrounding us, studying the multiverse invites us to dream of infinite possibilities. Although we still do not have direct evidence, the theory of parallel universes pushes us to explore the limits of our understanding and imagine realities beyond our existence. Each theory and model invites us to open our minds and question the barriers to our perception. Although the final truth remains elusive, studying the multiverse awakens our passion for discovering, looking beyond the stars, and embracing the immensity of the cosmos. In this vast and unknown universe, the multiverses offer us hope that excellent answers will be found in some infinite corner of space-time that'll expand our understanding of the cosmos and ourselves.